Okay, hello everyone. Welcome to a new video series where uh, I'm going to talk about minimal surfaces in R3 with a complex analytic approach. So my notes is based on a very nice textbook by Professor Yi Fang from Australian National University. It is a pretty standard book. It was published in 1993. And the thing about I love about that book is that he um, explains the terms very carefully, and he really go all his way to do the computations very carefully, which is very nice for self-studying. All right, and okay, so for the first talk, I'm gonna talk about minimal surfaces in R3. Note that this is going to work for arbitrary dimensions, Euclidean spaces, but for the sake of the sake of sake convenient, I'm gonna just talk about minimal surfaces in R3. Okay, so a minimal surface in R3 is an orientable, conformal, and harmonic convergence from a two-dimensional smooth manifold into R3, right? So now I'm gonna explain explicitly what are these terms: conformal, harmonic, and emergent. Okay, so first let's talk about conformality. Let's see if I have, yeah, I've okay. So when we say that an immersion is conformal, it means that at every point P on the manifold, there exists a chart around P such that the tangent spaces, the tangent vectors, um, uh, that is the derivative of the map with respect to U and V, um, it forms an orthogonal basis of the tangent space. And we also require the two tangent vectors to be equal in length, right? Such a chart is called an isothermal coordinate chart. Uh, well, this actually is not something very distinctive about minimal surfaces. We can actually do this intrinsically on every Riemannian manifold. Uh, they are called Riemannian normal coordinates. And so at first glance, this looks very mysterious, but it's actually not something that is very special about minimal surfaces. Okay, so an immersion is a map such that the differential of that map at every point is a linear embedding. That is, it is linear and it is injective. Okay, so it is pretty fundamental. We require this so that we can pull back the metric of R3 into our smooth manifold extrinsically. Okay, so um, about harmonicity, which is the most interesting property of this, uh, which is that the connection Laplacian of x is the zero vector. Um, so since we are having an immersion into R3, this connection Laplacian can be written down in a very familiar way, which is d square x du squared plus d square x dv squared equals to 0. Or another way to term this is that mm, the component functions of the map X are harmonic in this sense, right? Okay, so here's the fun fact. Yeah, the fun fact, I've already talked about it above, which is that we can always construct isothermal coordinate charts on any Riemannian manifolds. So the fact that distinguishes minimal surfaces is that under this particular atlas, X is harmonic. Okay. So now let's talk about complex analysis. That is the Riemann surfaces. Okay, so first I'm gonna talk a bit about Riemann, two different ways to talk about Riemann surfaces. So the first one is that they can be regarded as one-dimensional complex manifolds. That is Hausdorff, second countable, and locally homeomorphic to to an open set in the complex plane. And we also requires the two charts to be holomorphically compatible. Okay, so we can do the analysis. So that's the first way. And the second way is to start with a two-dimensional smooth real manifold plus a complex structure. A complex structure is an endomorphism from the tangent bundle into itself, such that J square is equals to minus the identity. So you can easily see that this endomorphism is born to replace the complex unit I. I mean the imaginary unit I, right? So these two definitions are actually equivalent. To go from this side, the green side, to the blue side, is actually very straightforward because we can just define an endomorphism by the multiplication with I, the imaginary unit, and every Cn is a homeomorphic to R2n, so this part is also um, guaranteed. But going from the blue side to the green side is not very trivial. We're gonna use the Cauchy-Riemann equations to prove it. Uh, yeah, so it is a very nice differential geometry and complex analysis exercise. Okay, so now let's get into the details. Let X be an immersion of an orientable surface into R3. And now, instead of writing the isothermal coordinates as U alpha and V alpha, I'm going to write it as Z alpha, where Z alpha is U alpha plus I V alpha, where I is the imaginary unit. Well, actually, I'm abusing the notation here because we are starting with a real manifold, and then we try to multiply it with a complex number, which is a bit weird. So a good rule of thumb that I think everybody learns from complex analysis is that if at first you're not very comfortable with uh, just inventing a real a number I um, and then make it to be the square root of -1. We can think of this space C as R2 with a multiplication and addition rule, so which makes it into a field, and then define I to be the 90-degree rotation, which is the matrix 0, 1, -1, 0. Okay, so I think that is the complete description of this. But for the sake of brevity, I'm going to just use this notation, which I think is harmless once you got used to it. Okay, so now let's go into the details about what I just said to show that this complex atlas, that is this smooth manifold with a complex structure, is holomorphically compatible. So to show that something is compatible, we just get two charts and get two charts that are non that are not disjoint. That is, they have a non-empty intersection, and we're gonna show that the map, the foot point map, is gonna be holomorphic, right? So now, so first we write W as x plus iy and z as u plus iy. The target is to show that z composed with W, the inverse of W is a holomorphic map. So this map maps the complex number x plus iy into the complex number u plus iv. So I'm gonna break this map down into two parts. The first is its real part, which is I'm gonna use the notation U, and the imaginary part, which is a V. Right. So the map U plus IV is a holomorphic if and only if it satisfies the Cauchy-Riemann equations written in this complex formula. Okay, this is a pretty standard fact from complex analysis. So our main objective switches to proving this Cauchy-Riemann equations. Okay, so just do the derivative and computations, and things will get clear. Okay, so first, by the chain rule, we differentiate capital X with respect to the variable X, and we got this expression. And the capital X with respect to the variable Y, and we get this expression. Okay, so we have to be careful here that the derivative, this in pinks, they are vectors, and this in green, they are scalars. So when you talk about when we talk about norm of these vectors, we are talking about we are going to do our arithmetics with the scalars, not the vectors. Okay, so be careful about that. Okay, so since these two charts are conformal, we have two very nice relations here. So the first one came from the fact that yeah, so these are the scalars, right? So yeah, it's the usual Euclidean norm from that we learned from high school. And the next thing is that they are orthogonal. So we have this very nice relation. Okay, so now let us square the left-hand side of this Cauchy-Riemann equations and see what we have. Okay, after squaring and computing using the fact that I squared is -1, we have this expression. And now we're going to substitute these two relations into this formula and replace all the u with y. I mean with v. Okay, so du dx is going to be dv dy, du dy is going to be dv dx, and the same goes for these two. And we squish them back again, and we get this formula. But we're not done yet, because there are two possibilities here, is that these two are equals, or one is the negative is of the other, right? So I'm gonna show that, so we have to show that the negative sign must not be there. So how do we do it? The contradictions, all right? Contradiction. Okay, so so suppose contradictorily that there is a minus sign there, and I'm gonna compute the Jacobian matrix, which is the matrix of the coordinate transformation. Okay, so because the minus sign is here, it leads to two minus sign here. Okay, which sorry, well, which shows that this derivative, I mean this determinant is negative, which contradicts the fact that this manifold is orientable. That is, these two charts are orientable compatible, right? So the minus sign must not be there, and so we have this Cauchy-Riemann equations. And yeah, so that is the proof. It's very technical, but it's actually very elementary if you've learned complex analysis and a bit of differential geometry. Okay, so uh, let's um, let's do something fun with derivatives and see what it looks like to talk about harmonicity on Riemann surfaces. Okay, so if we keep doing the derivatives of a capital X with the variable X, we have this formula which looks quite messy. And if we do the same thing for the Y variable, we also have this messy um, formula. But when we plus these two together, what will happen? Well, we have this, um, which looks like the Laplace equation of U and V. And so if we require it to be harmonic, then U and V must also be harmonic, which is pretty interesting, I guess, for first learners. Now here's an interesting corollary of minimal surfaces is that there is no closed minimal surface in all three. Closed here means that it's compact without boundary. The proof is very simple. We use maximum principle, showing that which says that a function cannot attain its local maximum in the interior of a domain. The maximum is always attained on the boundary. But since we require the boundary to be empty, it's not going to have any local maximum. So it has to be a constant function. So this map shrinks a whole surface into a single point. So that cannot be an immersion, right? So there can be no closed minimal surface in all three. Okay, so that is a very nice example. The same thing also happened is that there is no holomorphic immersion of a closed complex manifold into Cn. So we have to work with the projective space. Okay, so that is the end for today. Goodbye and see you next time.